Hello students, welcome to the next session. In the last session we have seen some classifications like Bohr's classification, SP, DF, block classification and so on. So finally we'll see at the long form of periodic table. With this we will be concluding all the different types of classifications so that we can move on to the properties and various trends across a period and a group. Extended or long form of periodic table, in this case what we have done is we have classified all the elements into periods and groups. SP, DF, block, that is also found here, but for convenience we have called them as periods and groups. Across these are periods and down we call them as groups. So previously they used to call them as rows and columns, but now we have to call them as periods and groups. Altogether in the periodic table we have 7 periods. Just remember 7 periods. 7 days a week, 7 periods in a periodic table. And there are 18 groups altogether. So let us look at the different periods and the number of elements that are being accommodated. Look at this table carefully. Altogether there are 7 periods, so I have given 1, 2 up till 7 periods. And what is the energy level that is being filled up? Suppose if I choose the first period, the principal quantum number, here n refers to the principal quantum number, the first principal quantum number is filled up. When I go to the second period, second, third period and third, and so on. In the first shell, in the first period, in the first shell we have S, 1s. Okay. Now in the second period we have filled up 2s and 2p. So altogether the valence shell is second shell, we have 2s and 2p. S and p, it will take up 4 orbitals, 4 into 2, 8 electrons. Therefore we have 2 plus 6 electrons. So altogether there are 8 electrons in the second period. The first element and the last element of the period, the first element of the first period is hydrogen, the last element is helium, whereas in the second period it is lithium and neon. Okay, so this is the first group, this is the 18th group that you have to remember. Hydrogen, lithium, sodium, potassium, rubidium, cesium and francium, first period. Helium, neon, argon, krypton, xenon, radon and oganesson, 18th period. So in the beginning class I gave you a memory trick. You might have got the trick. The trick itself is memory. So you have to memorize all the periodic elements, and the best way to memorize is along the groups. Okay, so let us move on to the third period. Third period, n will be 3. So we have 3s and 3p only. 1s and 3p orbitals altogether making up 8 electrons. Therefore we have 8 elements added. N equal to 4, we have 4s and 4p as the valence shell. 3d becomes the penultimate shell. This is the penultimate shell. So along with 4s, 4p, we will be having n minus 1d. Here n minus 1, n is 4, so we will be having 3d. It will be beginning from 4th period. 3d will begin from 4th period. Therefore we have d orbital inclusions, 5 d orbitals, 10 electrons. So 8, this will be 18. In the 5th period we have 5s, 5p and 4d. Again penultimate shell, n minus 1d. So we again have 18 electrons altogether, 18 elements in the periodic table across a 5th period. When we move to the 6th period, n equal to 6, we have valence shell 6s and 6p, penultimate shell 5d, anti-penultimate shell 4f. 4f, f will be beginning from 4 only. It will be beginning from 4 only. It can't be, you cannot have 2f, 3f, you cannot have 1d, 2d. You can only have 3d, you can only have 4f. That you will be understanding clearly in the atomic structure. Right. And in the last period we have valence shell 7s, 7p, which are taking up 4 orbitals, 6d plus 5 orbitals, 5f plus 7 orbitals. So 6th and 7th period, altogether they are accommodating 32 plus 32. 32 electrons and 32. So altogether the number of elements will be 2, 8, 8, 18, 18, 32 and 32. This is what you have to remember as a magic figure. For 7 periods the number of elements are 2, 8, 8, 18, 18, 32 and 32. Okay. 288, 18, 18, 32 and 32. That is the number. In the beginning, while giving you the table also, how to get number. Suppose if I take hydrogen to lithium, the difference will be 2. From lithium to sodium, the difference will be 8. From sodium to potassium, the difference will be 8. So if you just go on taking these numbers 2, 8, 8, 18, 18, 32, you can get the atomic numbers of the first group. Okay. Right. So let us move to the next step. In the starting, I told you there are two different types of classifications of periods and groups. I mean, especially for the groups. One is American style and another one is IUPAC style. In the American style, we have A, B along with the Roman number. So we will be taking a Roman numeral. That Roman numeral will be associated with A or B. 1A, 1B, 2A, 2B and so on. So here I have given American and IUPAC nomenclature. For example, 1A, 2A, 3B. You just remember 1A, 2A. After 2A, you are getting 3B. Directly you are not getting 3A. 3A will be like P block element in the periodic table. So 3A is starting here. This will be like starting with boron. This will be like scandium, titanium, vanadium, chromium, manganese. 8B is a group. It is not just one period. I mean, it is not just one group, but it is a group of groups. It is a group of 3 groups. It will be having iron, cobalt and nickel. Along with the IUPAC numbering, if I give 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is coming under 8B. Okay. According to American style, 8B refers to group numbers 8, 9 and 10. Iron, cobalt and nickel, or iron, ruthenium, osmium, cobalt, rhodium, iridium, nickel, palladium, platinum. All of them belong to 8B. So try to remember this. Then later on again we have 1B and 2B. So this will be like copper and zinc. Copper elements, copper, silver, gold, zinc, cadmium, mercury, they belong to 1B and 2B. They did not start 1B and 2B here. They did not start 1B and 2B. They have started 1B and 2B here. Later on, 3A, 4A, 5A, 6A and so on. So that is American style. You have to remember both. You have to remember A, B type of classification. You should also remember 1 to 18. AB is also very simple. 1A, 2A, S block. Then you come to P block. For P block again 3A up till 8. Then you go to D block. D block will be starting from 3B, 4B, 5B, 6B, 7B, 8B. 8B, it is a group of 3 groups. Then will be 1B, 2B. Okay. That completes the D block also. F block, it is placed separately. Right. And for the periodic table easier classification, they just called it as, instead of calling them as S block, P block, D block, F block, they call it as left portion, right portion, middle portion and bottom portion. Left portion is like S block element, right portion is like P block element, middle portion is D block element and the bottom portion is F block elements. Okay, so this is another type of classification, the long form of periodic table. There are a few common names for some groups. This you have to remember. When we discuss individual groups, you will come to know why they got those names. But just for the explanation point of view, what are the various groups and what are their family names? 1A group, very commonly we call it as 1A group. We generally don't call it as first group. We call it as 1A group, 2A group. So 1A group, these are also called as alkali metals. 1A group are called as alkali metals. 2A group are called as alkaline earths or alkaline earth metals. Alkaline earths or alkaline earth metals. 5A group are called as pnictogens. P should be silent. 5A group or 15th group is called as pnictogens. 6A group or 16th group are called as chalcogens. Chalcogens. 7th A or 17th group are called as halogens. Then 0 group or 18th group are called as noble elements or inert gases. Noble elements or inert gases. 2B or 12th group are called as zinc metals. Zinc, cadmium, mercury and copernicium. 1B or 11th group are called as copper metals. Copper, silver, gold and copper, silver, gold and rhodium. Okay. So you just go through these elements. What are the elements that are present in each of these groups? And these you have to remember. So suddenly if I ask you what are halogens, you should be able to answer fluorine, chlorine, bromine, iodine, astatine. Okay, fluoro, chloro, bromo, iodo, astatine, and tennessine. Tennessine is also included, but for chemistry purpose, most of the chemical properties are not discussed for tennessine. So you can just remember up to fluorine, chlorine, bromine, iodine, and astatine. Okay. And finally, coming to the what are the advantages of the long form of periodic table and drawbacks. Advantages and drawbacks, both we'll see. What are the advantages? First one, the position of the element in the periodic table is governed by electronic configuration. So wherever I am placing the element, that element place is governed by its electronic configuration. According to electronic configuration, I am numbering the elements. Number 1, 1s1. Number 2, 1s2. Later on, 1s2, 2s1, 1s2, 2s2. So according to their electronic configuration, the elements are placed. That is a very, very convenient type of classification. No problem as such. So this is showing a gradation in the physical and chemical properties. So that as I am increasing the electronic configuration, that is also showing some gradation. Later on we have classified them into groups also. So with the help of these groups, I can very easily understand the physical and chemical properties. That is a big advantage of this long form of periodic table. We have also divided them into left, right, bottom portion and middle portion, or you can classify them into S block, P block, D block and F block elements. That has made to understand the chemistry of these elements very easy. Okay. And one more point is, suppose if a new element has been discovered, the new element has been discovered, its valence shell electronic configuration is NS1. If valence shell is NS1, I directly put it into 1A group or first group. The valence shell electronic configuration is NS2 NP6. I directly take it and put it into inert gases or noble gases. Okay, so by knowing their valence shell electron configuration or valence electron configuration, I can directly place that element, whatever new element that we discover, into a particular group. That is the biggest advantage of the long form of periodic table, where we have classified them into 7 periods and 18 groups. Right? Any disadvantages of long form of periodic table? Yes, there are some disadvantages, or you call them as drawbacks. Hydrogen, it behaves like 1A group elements and also like halogens. So should I place it under 1A group or should I place it under halogens? Where should I place it? That is a big confusion, but for convenience purpose we have placed it under 1A group. That is a drawback, because some scientists argue that it has to be put under halogens because it also behave like halogens. But anyway, based on its electron configuration 1s1, we have kept it under 1A group. So that is one drawback. Second drawback is, you might be aware of the inert gases. All inert gases will end with valence configuration NS2 NP6 except helium. Helium is 1s2. So helium is 1s2, so immediately I have to put it under 2A because it is S2, NS2. But we are not putting it under 2A, we are putting it under the inert gases, 18th group. That is another drawback. Right? Third drawback, we have lanthanides and actinides. But these lanthanides and actinides, they are not given a proper position. They are placed at the end of the periodic table, at the bottom portion of the periodic table. So that becomes another drawback. Position of hydrogen, position of helium, position of lanthanides and actinides. These are the 3 important drawbacks. Classifying into A and B type, that is not exactly a drawback, but it was for convenience. Later we have converted into 1 to 18. 1A and 2A we are still following now. Okay, 1A, 2A or 1B, 2B type of classification we are still following. That was a little bit drawback, but we have to study it. Okay, now mostly it is used in all text. We very commonly use 1A, 2A group of elements. Instead of saying first group, second group, 17th group or 18th group, we say halogens, or we use the term 8th group. or we use the term 1B, 2B, 3B and so on. Okay, these are the drawbacks. So this is all about the various types of classifications. We can also have a classification based on the metals and non-metals where Lavoisier has done, but I'm not discussing the classification into metals and non-metals because we are aware we have studied them under the first A group or second A group, or whenever I was discussing about D block elements, what are the important characters of metals and what are the characters of non-metals we have discussed. So that becomes another type of classification where we give the characters of metals separately, characters of non-metals also separately. Okay, that will come in the form of notes. We need not explain it again, but it will be coming in the form of notes for you. Let us work out a few questions. The electronic configuration of an element is 1s2, 2s2, 2p6, 3s2, 3p3. What is the atomic number of the elements which is just below the above element in the periodic table? So for every question, take a little time or pause the video and then try to answer it. What is the strategy that you have to apply? The strategy that you have to apply is 1s2, 2s2, 2p6, 3s2, 3p3. So altogether it is 6 plus 2, 8 plus 2, 10 plus 2, 12 plus 3, 15 electrons. It is present in third period. It is present in third period. What is the next element? It means what is the element in the fourth period. So just now I explained 2, 8, 8, 18, 18, 32. If I want that fourth period, you add 18 electrons to this. So you add 18 to this. 18 to this means this is already atomic number 15. I am adding 18 to this, so that becomes 33. That becomes 33. So what is the element that is coming below this element? The answer is 33. So what is that element? 33. 33 is arsenic. Nitrogen, phosphorus, arsenic, antimony, bismuth. Okay, so that should be your approach. Simply you have to add 18. Why are you adding 18? Because this belongs to third period element. We want a fourth period element. So accordingly you are doing it. Okay, so let us move to the next question. A transition element. So it belongs to D block. X has the configuration argon 3d5 in its +3 oxidation state. It is belonging to which group? A transition element X has some configuration argon 3d5 in its +3 oxidation state. So some metal is present in its +3 oxidation state. Its configuration is argon and 3d5. Argon is 18 electrons, 18 plus 5, it is 23 electrons. It is present in +3 oxidation state. If I go for its elemental state, 0, it means I have to add 3 more electrons. I have to add 3 more electrons. Directly I cannot put 3d8 because whenever I am removing the electrons from transition element, we remove it from S and then we come to D. This you will be understanding when you go to D block elements and coordination chemistry. Okay, these are transition elements. The valence shell will be 4s. So here when I have given 3d5, it will be like 3d5 4s0. Now in this case it will be 4s2. So 3 electrons, 2 electrons we have filled them in S2, 1 electron you fill it in D, already 5 electrons are there, 5 plus 1, so altogether it is becoming 6. It means the same metal, if it is in its elemental state, it has argon 3d6 4s2 configuration, 3d6 4s2. When I say 3d6 4s2, forget about argon, 6 plus 2, 8. 6 plus 2, 8. So where does it belong to? Valence electrons. Valence electrons are 8. Therefore it has to belong to 8th group. How many valence electrons are there? 3d6 and 4s2. You put it under 8th group. What elements are there in the 8th group? Iron, ruthenium, osmium and hassium. Iron, ruthenium and osmium. 3d, 4d, 5d. Forget about 6d. So this is belonging to 8th group, or in the American nomenclature it belongs to 8b. 8b will have iron, ruthenium, osmium, cobalt, rhodium, iridium, nickel, palladium and platinum. Okay, so that element is iron. Which one of the following pairs of atomic numbers represents elements belonging to the same group? What is the strategy that you are going to apply? They are belonging to the same group. So the difference between them, either it should be 2, 8, 8, 18, 18 or 32. 2, 8, 8, 18, 18, 32 or simply 2, 8, 18, 32. These are the 4 differences that you have to search for. Difference is 9. Difference is 9. So they can't be belonging to the same group. 13 and 31. 13, 23, 31. The difference is 18. So they can belong to the same group. 10 and 30. The difference is 20. They can't belong to the same group. 3 and 14. The difference is 11. They can't belong to the same group. So the option has to be B, because the difference is 18. Either 2, 8, 18 or 32. They belong to the same group. That is your strategy. Okay. So the option is B. An element with atomic number greater than 16, sulfur, greater than sulfur, and chemically similar to the element with atomic number 10 is. Similar to the element with atomic number 10 is. So it should be greater than 16 and it is similar to atomic number 10. What could be the element? The element should be greater than 16, similar to 10. What is 10? 10 is neon. 10 is neon. Similar to 10 should be greater than 16. So I go for argon, 18. Or you take any other argon, krypton, xenon, radon. Any of these elements you can take. That should behave like group element 10, neon. So the elements which behave like neon are helium, argon, krypton, xenon, radon and argonisn. And that should be greater than 16. So I can't take helium. I have to either take argon, krypton, xenon, radon or argonisn. Okay. The properties of the elements are the periodic functions of their atomic numbers. This statement was given by Bohr, Niels Bohr, or Dobryner, or Mendeleev, or Moseley. Well, you are aware with the discussion has been done. It is Moseley. Atomic numbers. If it is atomic weights or atomic masses, that was by Mendeleev. Dobryner's law of triads. And Niels Bohr has given classification. He has not given any law for the periodic table. He has not given any law, but he has given a classification into 4 types. We have studied those 4 types also. The first element of the rare earth elements, rare earth metals. What is the first element? You will be coming in the F block. You will be getting this in the F block. The first element will be cerium. Okay. Element in the same vertical group of the periodic table, elements in the same vertical group of the periodic table will have the same number of electrons, same number of valence electrons, same number of atomic numbers, same electronic configuration. So elements belonging to the same group will have, what will be same for them? Number of electrons cannot be same, because for every element the number of electrons increase. Atomic number, same vertical group, they cannot have same atomic number will be different. Number of valence electrons, electronic configuration will change. Suppose if I take, say, hydrogen is 1s1. After hydrogen we have lithium, 1s2, 2s1. Electronic configuration is same, but the valence electrons are same. You just check, 1s1, valence electron is 1. Then lithium, 1s2, 2s1, valence electron is only 1. Then you take sodium, 1s2, 2s2, 2p6, 3s1. In the third shell, there is only 1 electron. So the valence electrons are same. Okay? Number of valence electrons are same. The option is going with C. An element with atomic number 20 is placed in which period of the periodic table? An element with atomic number 20 is placed in which period? 20 means calcium. Calcium is in which period? Then the easiest strategy to follow, does it belong to third period? Does it belong to fourth period? What is the strategy to follow? First write down its configuration. 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So the valence shell is 4s2, therefore it belongs to fourth period. Okay? It is 4s2, therefore it belongs to fourth period. As simple as that. So calcium belongs to fourth period. This is classification into metals and non-metals. That is very easy, but the one thing that we have to see is what are the different types of metalloids which are present. Previously it was 5 metalloids, but now 8 metalloids are approved. So you can see what are these metalloids. Boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine is also included now. Previously astatine was not included. In the beginning, silicon, germanium, arsenic, antimony, and tellurium, these were only the 5 metalloids. Boron was also not there. But now even boron is included. Polonium and astatine are also included into metalloids. These metalloids, we can see that you can use them in the computers, audio systems, TV receivers. Right? Silicon you might have seen at many places, silicon and germanium. In the electronics, very commonly we will be using this silicon. And lastly, there could be a question where an element can be given and they can ask to which group does the element belong to. So one question that they can ask is, they can give you an electron configuration. Based on the electron configuration, to which group does it belong to? One easiest way, you just count the valence electrons, and based on those valence electrons you can put it under that particular group. Or sometimes the question may be twisted. So in such cases we have a small methodology. The small methodology is, first of all you have to check whether d orbital electron is present or absent. You just check whether d orbital electron is present or absent. We have two cases. There could be element where d orbital electron is absent, okay, or d orbital electron could be present. Whether it is absent or present, the next thing that you check is how many electrons are present in the last orbit. Is it the last orbit is having either 1 or 2 electrons, or is the last orbit having greater than 2 electrons? In both cases the same classification. Last orbit, is it having 1 or 2 electrons, or is it having greater than 2 electrons? Okay, so if d electrons are absent, last orbit with 1 or 2 electrons, last orbit with greater than 3 electrons, or greater than 2 electrons. If d electron is present, last orbit with 1 or 2 electrons, last orbit with greater than 2 electrons. Greater than 2 electrons means greater than or equal to 3 electrons. Greater than or equal to 3 electrons. So what is its group number? Simply last orbit, if it is with 1 or 2 electrons and d orbital electrons are absent, simply remember the group number will be the number of electrons in the last orbit. The number of electrons in the last orbit. So how many number of electrons are present in the last orbit, that you have to count. When the d electrons are absent, second point, when the valence electrons are either 1 or 2. When d electrons are absent, but if the valence electrons are greater than 2, it could be 3, 4 or 5. Then count the number of electrons in the last orbit, just as you have done it for here, the number of electrons in the last orbit plus 10. Simply add 10. Number of electrons in the last orbit plus 10. Okay. Next. Suppose if d electrons are present, the same methodology again we are following. Last orbit with 1 or 2 electrons, last orbit with greater than 2 electrons, or it is equivalent or greater than 3 electrons. Then how many electrons are there? It is the number of valence electrons, or just like the previous one, it is the total of electrons present in the last orbit plus not 10. Here the number of d electrons must be added. The number of electrons in the last orbit plus the number of d electrons. Previously the number of electrons in the last orbit, group number. Next one, number of electrons in the last orbit plus 10. But now number of electrons in the last orbit plus number of d electrons. Okay. And in the last case, it is the number of electrons in the last orbit plus 10. So whether the d electron is absent or present, if the last orbit is having greater than 3 electrons, group number is same for this, number of electrons in the last orbit plus 10, number of electrons in the last orbit plus 10. Okay. But if it is 1 or 2 electrons in the last orbit, then group number is number of electrons in the last orbit, number of electrons in the last orbit plus number of d electrons, because it is already having d electrons. Let us understand by taking an example. Whether it is lanthanides or actinides, they belong to third group. This you have to remember. Lanthanides or actinides belong to third group only. Lanthanides belong to 6th period, actinides belong to 7th period. Lanthanides 6th period, actinides 7th period. Both belong to third group. Lanthanides and actinides belong to third group. Just keep it in mind. Lanthanides and actinides belong to third group. Lanthanides 6th period, actinides 7th period. Okay. Helium is an exception. Why helium is an exception, we'll understand. Suppose if I take helium, helium is 1s2. So the last shell has 2 electrons. It has no d orbital. So d electron is, no d electron. D electron is absent. Last orbit is with 1 or 2. Then what is its group number? The number of electrons present in the last orbit. So I cannot put it under group 2. Because if I put it under group 2, I will be wrong. It is belonging to group 18. Therefore helium is an exception for this classification. Okay. Helium is an exception. Now let me take, say, sodium. I am taking, say, sodium. For sodium, the electron configuration is 1s2, 2s2, 2p6, 3s1. Last orbit with 1 or 2 electrons. This is the last orbit. It is having 1 electron. It can have 1 or 2 electrons. Okay, it is having 1 electron. If the last orbit is with 1 electron, no d electrons are present. What is its group number? The number of electrons present in the last orbit. The number of electrons present in the last orbit. Therefore, sodium belongs to first group. Sodium belongs to first group. It is as simple as that. Suppose if I take neon. Why am I taking neon? Electron configuration is 1s2, 2s2, 2p6. Neon is 1s2, 2s2, 2p6. Last orbit should be greater than 3 electrons. Last orbit, not the last orbital. Last orbit. Orbit means second one, second shell. Don't just consider 2p. You have to consider 2s and 2p because it is last orbit, not last orbital. Okay, so you have to consider second shell. Second shell has S subshell and P subshell. S is having 2 electrons, P is having 6 electrons. In such a case, what is the group number? The total number of electrons in the last orbit. Last orbit has 8 electrons plus 10. Group number is 18. Suppose normally if I consider 2s2 and 2p6, the number of valence electrons are 8. Immediately if I put it under 8th group, I will go wrong. Because previously when we discuss about manganese or iron, For that iron we have say 8 electrons. Directly I can put it under 8th group. But even this is having 8 electrons. I cannot put it under 8th group. We have to put it under 18th group because this has no d electrons. The last shell has greater than 2 electrons. Therefore you add 10 for that. You remember this table. You write it at least 5 or 10 times, no issues, or even if you write for 15 times, no issues. But simply 2 classifications, one d electron absent, one d electron present. Second classification is either the last orbit is with 1 or 2 electrons greater than 2 electrons. Last orbit is with 1 or 2 electrons greater than 2 electrons. Then the group number is the number of electrons present in the last orbit, number of electrons present in the last orbit plus 10. Next case, if d electron is present, number of electrons present in last orbit plus the number of d electrons, number of electrons present in the last orbit plus 10. Okay, so 2 examples we have done. For this, let me take any element like maybe I'll take manganese. Let us take manganese. For manganese, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s2, 6, 7, 8, 9, 10, 18, 20, 25. Manganese is 25. Last orbit with 1 or 2 electrons. Is the last orbit with 1 or 2 electrons? Last orbit here is 4s. Fourth shell. Fourth shell is the last orbit. It is having only 2 electrons. Is it having d electrons? Yes, it is having d electrons. Then what is its group number? Sum of the electrons in the last orbit. In the last orbit we have 2 electrons plus the number of n minus 1 d electrons. 4s is the last orbit. N minus 1 is 3d. 5 electrons are present in it. 2 plus 5 is 7. So manganese belong to 7th group. Suppose if they give iron 3d6 4s2, then 2 plus 6, iron belongs to 8th group. Okay. Now maybe here I'll take say gallium. I'm taking gallium. Gallium is having electron configuration of 31. Sorry, atomic number of 31. So what is its electron configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p1. Okay, that is gallium. So 6, 7, 8, 9, 10, 18, 20, 30, 31. Do you have d electrons? Yes. The valence shell, is it having greater than 2 electrons? Yes, because the valence shell is 4th shell. It is having greater than 2 electrons. It is 3 electrons. Then what is the group number? The number of electrons present in the last orbit. 2 plus 1, 3. The number of electrons present in the last orbit plus 10. It means gallium should belong to 13th group. Okay, gallium should belong to 13th group. Right? So this is how we are classifying whatever element that they have given. Accordingly, you can put it under that particular group, whether d electrons are absent or present, and what are the number of electrons present in the last shell. You have to count whether it is 1 or 2 or greater than 1 or 2. Later on you have to check for the n minus 1 d electrons, or you have to add 10 and so on. Right? So this is all about the basics and classifications of periodic table. From the next session, the most important part of periodic table, we have to discuss the trends in the periodic table. That we will be doing in the next session.